The internet connection is stable, right?
Yes, yes. No
okay,
issue.
cool.
You're okay with recording the...
Yes, I'm okay with recording, yeah. Not a problem, yeah.
Hello everyone, welcome to this week's first string seminar. Today we are very happy to have Amit from IMSC, and he'll tell us about positive geometries, Corolla Polynomial and gauge theory amplitudes. Over to you.
Thank you, I'm happy to be here, and as some of you might not know me, I'm Amit. I'm a grad student at IMSC, and today I will talk about positive geometries and how we can have gauge theory amplitudes out of there. Okay, so this is a work that did with Alok, okay, Alok from CMI. So to begin with, I will briefly talk a little bit about what is the program of positive geometry itself. So I would say that it all started with Andrew Hodges realizing that a certain amplitudes in pure gauge theories, no supersymmetry, nothing, certain amplitudes are actually volumes of certain polytopes, okay? So this was a remarkable result, and it was in 2009, and these polytopes lived in twistors, CP3 coordinates and everything, and this was a crucial step towards the discovery of the amplitude-hedron, okay, which came out in 2013, Arkani-Hamed and Trunka, which got, obviously, you might all have heard of the amplitude-hedron. So as of now, till this point, what might be happening was this, that we have the usual QFTs, and these beautiful structures, these neat structures are coming out of them, okay? And the amplitude-hedron turned the idea upside down, that can we have locality and unitarity emerge out of some more primitive ideas? As in, we say that can we just do something else and get amplitudes out of them, and then call that as a unitarity and locality, okay? So what property should an arbitrary function of external kinematics have to be deemed as a sensible QFT amplitude, okay? And I would say another big question can be that, is this program restricted to only certain class of theories, or can one have garden variety QFTs out of positive geometry? So if you tell me that can you get standard model with arbitrary set of matter particles in it out of a positive geometry program, okay? So yeah. So a little bit of more history. So after the amplitude-hedron, positive geometry description for scalars has been developed over the years. I haven't cited a lot of names here, but Neem Arkani-Hamed, even Alok Ladda, Tranka, Songhe, and a lot of people have worked on it over years. Okay, but even though the original construction due to Hodges was for pure Yang-Mills, the pure Yang-Mills theory had resisted the integration into the positive geometry program. What that means is that starting from some ideas, can you get the Yang-Mill amplitudes? Not some particular amplitudes, not just MHV or NMHV, can you get all amplitudes, okay? And so this question didn't have a very good answer till last year, and very recently Arkani-Hamed et al. Discovered a one way to get Yang-Mills from positive geometry. This has been a lot of papers around December and after that, and we proposed another way to obtain Yang-Mill amplitudes, pure Yang-Mill amplitudes, no stringy deformation, no supersymmetry, and using the positive geometry of scalars and the so-called Corolla differential operators. So we'll talk about that. Yes. Yeah. Okay. So I've structured the talk like this. We'll talk about just tree level at the beginning, but we can do it at loops, but it is just so that I can communicate some idea, and then afterwards we'll talk about loops, okay? And in the end, we'll have something like we'll do these things in the Schwinger parameterizations, which is now called the curve integral formula. If we have time, we'll get there. Yeah. So to begin with, a very quick review of whatever is associahedron. I'm sorry, I won't have much time to go into the details of this, but the associahedron is a set of relations between the triangulations of an n-gon, okay? So what that means is that you take some, for instance, if n is equal to 4, you take quadrilaterals, and then you triangulate it, okay? You keep drawing diagonals in it, and that will be the triangulations. And associahedron is a set of relations between these triangulations, okay? So a partial triangulation with k chords form a face of codimension k, okay? So what does that mean? What are the maximum number of chords that an n-gon can have? That is n minus 3. Mutually non-intersecting curves, okay? Mutually non-intersecting chords, yeah. So if you draw all of them, then what you get is a codimension n minus 3 face, okay? And this a n minus 3, the associahedron, it is an n minus 3 dimensional object, okay? So codimension n minus 3 in a n minus 3 dimensional shape is a dimension 0 face, that is a vertex, okay? So a complete triangulation of an n-gon gives you a vertex, okay? And you can see that here. So here's the simplest example, A1, that is for n is equal to 4. So if you take a quadrilateral, there are only two ways you can completely triangulate it using only a single chord. And these two will be the vertices of this. And inside, in the polytope, two vertices are adjacent if they differ only by one chord. So what does that mean? That if you, let's say, start with this one here, if you keep one of this chord fixed and you change the other one, then you get this triangulation, okay? So these two shall lie on the two adjacent vertices of the associahedron, yeah. And why do we care about this? Because even pure graph theoretically, what we can say is that a complete triangulation of an n-gon is dual to a trivalent graph. Simply connected just means that there are no loops in it, okay? Simply connected as in topologically simply connected. So an example just to illustrate the idea, it's this. So if you take a hexagon, and if you have this kind of a complete triangulation of it, what you can do is put a vertex as in just a graph theoretical vertex inside each of the triangle, and what you get is this tree graph, all right? Yeah, so now, so that's why you can see that it will have something to do with phi cube theory, okay? Or any trivalent interactions in a way. So we'll see that it can also be seen as gluon interactions as well in some way. We'll get there. So what we can do now is we can associate a sign to each of this vertex of the associahedron. So vertex of the associahedron is a complete triangulation, okay? We can assign a sign to each of the vertex and such a way that it gets flipped upon a mutation. Mutation means changing a single side. That means if you have this graph, okay, You can imagine this as a complete triangulation of a 6-chord, just like this, exactly. All right. And now if you mutate it, mutate means that if you change one of the particular chord, then you get this graph. And I will just say that if you have assigned a +1 sign to this one, you assign a -1 sign to this one. Okay. So why do you care about sign? Because we want to define a scattering form or a canonical form, and this is how you'll define it. That let us associate the following differential form to a particular graph. Okay. So let's say if we have this graph, I don't want to say this line, but it is, in one way you can say that, okay, it's like blasphemy to say, but it is a neat way to arrange all the Feynman graphs.
Is it really a neat way? Is that clear? That somehow this associahedron is a way to actually arrange the Feynman graphs?
No, that's not why it started. People weren't trying to place all the Feynman graphs neatly somewhere.
Yeah.
What they were just doing was that, I mean, you can start with the combinatorial associahedrons. You can realize it in some kinematic space, okay? And what comes out of that is that these chords literally becomes the propagators, okay? So the idea from there is that if you find the volume of that associahedron, then you will get the amplitude itself.
I mean, this is a little worrying. It's that, of course you have many kinematic invariants which are ki dot kj.
Yes.
So, and it's true that sum of ki is a polygon, and so you can think of that, but this seems to be a little too general, right? I mean, quantum field theory has some structure. So
yes.
I'm actually just asking you for some words. It's okay if it's imprecise, just for my understanding. Something I've never understood about the whole program is, kind of if we want something to work, we want some physical intuition behind it. It can't just be that, we find something from combinatorics and it'll magically become an amplitude. So what is the physical intuition?
So the physical intuition is in a way just this, that you can have these graphs and they're dual to the triangulations. And one thing that you said is that it just magically comes out to be phi cube theory. So over the years, what has now been realized is that it need not to be the unique phi cube theory, okay? So if you draw these associahedron in some non-trivial way in the kinematic space. Kinematic space means what? That for n is equal to 4, we will just have the Mandelstam variables, S and T. So if we draw this line in some non-trivial way, we won't get just the phi cube theory, but some amplitude of some other theory. Okay, maybe massive theories or deformed scalars in some way and all. Yeah. So I don't have a very good answer to like what is the intuition behind it. It's okay. Okay. Yes.
Maybe I can ask some
Yeah, I also have a slight similar confusion. Is this all specific to some specific dimension like d equal 4's amplitudes, or is this program a very general thing?
It's not for d is equal to 4 actually. That's the thing, yeah. Because as of now, all we care about is that you begin with a kinematic space. Okay, yeah. There's kinematic.
Can you understand scattering in non-relativistic situations this well as well, or?
Non-relativistic.
In that sense, I meant in a general setup.
I won't say non-relativistic.
Or quantum mechanics.
Because here, okay, let me say this, that what is it that we care about? Here we only care about that we want right poles. That's all that in a way we care about. We want to generate 1 over s plus 1 over t. Okay, naively speaking, we want to do that, okay? And if I say that, well, how can I get 1 over s plus 1 over t, is that 1 over s will be, in a way, 1 over x13, okay? Sorry, I'm jumping the gun, but it's fine. So the idea is that you want to associate the idea that there are the propagators and you want just the right pole, the pole structure. The pole structure can be related to the diagonalizations or the dissections of an n-gon. And that's roughly just the idea, yeah.
Am I right in understanding that you'll probably only get like 3-point interactions from this, because like at least the graphs you showed there in the next slide, the one that you got out of dualizing this triangulation, is it true that you'll always get like 5 cubed kind of vertices? Or?
You can guess easily that if you want, let's say, a 5-4 theory, you won't do a triangulation, but what might be called a quadratalization. I don't know what the word is. But people have done that, and that is easily doable. Yeah, that's not a problem.
So that was, and I had this other not so general question, which is that I didn't understand what you meant by this mutation. Like, what do you mean? So you take a complete triangulation and then do what?
By mutation, I just mean this, that let's say you have this chord, okay? Let's say you have this particular complete triangulation, okay? And I say, what are the possible mutations for this one? So what I can do, I can keep this chord fixed. What are all the other chords that I can draw? I want to change this one now. I want to exchange this one for something else. So and the only possibility is this one.
So do you just mean like you will take one particular triangulation and try to generate all the other triangulations from it?
In a way, yeah. If you just switch only one chord, then that's what a mutation is.
And what did that mean about the sign for the dual graph?
Oh, the sign just means that if I flipped only a single chord, then I flip a sign.
I see.
Okay, it will be clear. I have a detailed example. Okay, let me get here first. So for instance, if you have this one, okay, and you get from here to here by flipping a single chord, okay, so the sign for this one is -1, say, then sign for this one I will say is +1. Okay, so from here you get here by flipping a single chord again, so you get another flipped sign, and so on and so forth. Okay, yeah. So why do we do this? The idea is that you want to have a differential form that captures the structure of the associahedron. Okay, so associahedron is a relation between the triangulations, mean that it captures all the information about these mutations in it. Okay, so and this omega, the differential form that we've defined, it captures that via the sign of t.
This I are the edges of the graph?
I are the, yeah, let me say this, that the t is a triangulation. T is a triangulation means I will say that this is a T, okay? And this is a I, this is a I. T is a set consisting of all the diagonals. I's are the particular diagonals that you have inside it, okay?
So we call that 1, 2, 3, 4, 5, this is 1, 3. And
exactly, yes, we'll get there. So for instance, in n is equal to 4, what you will have is 1, okay, so there are only 2 chords possible. There are only 2 triangulations possible, 1, 3 and 2, 4, okay? And these two are related by a mutation in a way that you flip a single chord, okay? So you pick a negative sign. So what you have is this. So this is the omega, okay? And you can see that it is this, and I just claim, and it can be checked easily, that all the omega for arbitrarily n will be projectively invariant, okay? So that means if you scale all the xi by this, then your omega remains invariant. Okay. So for instance, here is a detailed example of n is equal to 5. So that means you have graphs like these. Okay.
Xijs are abstract variables.
Yes, as of now, Xijs are abstract variables. As of now, we're not saying that they're related to Mandelstam variables. Once you do that, that means you have drawn an associahedron inside the kinematic space of the scattering, okay? And that leads you to the usual getting scalar amplitudes from the associahedron, and I actually won't be doing that today because I want to get into another direction. Okay. So as of now, you can say that Xi's are just abstract variables. Yeah. So for instance, here you can see that, for instance, this triangulation is x13, x14. Okay. And now, how do you define this thing for it? You just take d log xi wedge d log xi, another one. So you have this one, d log x13 wedge d log x14, okay? And this sign you can choose arbitrarily. Let's say you pick up a plus sign for it. So then you flip it from here to here, and then you get a negative sign. Okay, now it is a 1, 3, 3, 5. Similarly, you get here, you flip a sign, you have now 2, 5, 3, 5, and so on. So you have a consistently 5 complete triangulations and 5 these forms, and then you can add them all up, and this is the omega for the n is equal to 5. Okay, it's a 2 form. It's a 2 differential.
The statement you're making is that this is invariant. The previous slide you
Yeah,
said that this is invariant under x going to some
yes,
scalar function.
yes. I mean, the idea is that you can write this omega as dependent only on the ratios. That's a simple algebra that you can check.
Which order are you picking the chords? Because in the previous
Right.
you need an order, otherwise the sign will be always ambiguous.
If you flip them, then you get an overall negative sign. And omega is defined only up to an overall negative sign. So you don't. Yes.
Along this pentagon.
Yes. Let me. I get the idea. Let's say that you start with this one, x13, x14. So by doing a mutation, I mean by flipping one, you exchange 1,4 with a 3,5. Okay. So you want to keep dx13 wedge something as fixed, dx13 wedge something, and 1,4 has been replaced by 3,5. That's why there's a negative sign.
But that's not happening here, right? Like
Yes.
when you go down.
That is why, because you flipped the.
Yeah, why?
That is why you flipped this one. It can be consistently done. Okay, let me say it.
1,4 has nothing.
Yes. Okay. Yeah. So if you flip that one as well, then you get this one. Yeah. So exactly. So so if you write this as d log x24 wedge d log x14, then you get a negative sign. That's the idea. It can be consistently done. Yeah.
Get the amplitude from here.
Scalar amplitude.
Yeah.
Okay. I will very quickly do that. Okay. So let me do it for n is equal to 4 because that's the simplest, almost a trivial case. Okay. So what you do is you say that I want to carve out a positive region in my kinematic space. So let me tell you what that means. That means this. Now these x's are the physical Mandelstam variables. As of now, I would have said that those are just some random things. And now this is what is usually called S, this is T, and I would say that this is U, okay? And this is also, minus greater than equal. All right, yeah. So the first inequality keeps us here.
Normally, in a chiral, one is positive, the other one negative, right?
Yes.
It will be S positive and T and U negative.
Yes.
But here you are taking S and T both positive.
Yes. Yeah. No, I think that's just the usual thing. Right. Yeah. Yes. Mm-hmm. No, that I understand. Yeah. So maybe the idea is that this is not actually the physical scattering. So if you say that I'm here, there won't be any scattering happening for this point. Okay. But in this region, you can still draw a line. Oh no, that's right. Oh, sorry, maybe I did this wrong. Okay. Oh, that much I agree with. That has to be 0. Yeah, that I agree. Yeah. So now what you do is, so this tells you that x13. Oh, sorry. And this I say is a constant. Okay. So this condition will tell you that x13 is equal to and so usually the point is this, that the first inequality keeps you in this region and the second inequality keeps you in this region, and this inequality gives you this. Okay.
That's what is drawn.
Yeah. Okay. Yeah. Sorry. Yeah.
Why are you setting U to a constant?
This in a way, this I would say is not a physical scattering data. Okay. These are some relations that carve out a region in the kinematic space, I would say. Okay, so if you say that if I'm here, what are the thetas and phis and angles for the scattering process, I would say that instead I would just, this is just a region in the kinematic space, okay? And what this is, it's a line segment, okay? And as we saw that A1 is a line segment, okay? Yeah, and from here, what I will say is this, that okay, and what I have is this. This was omega, and if I take omega and restrict it onto this one, I get this. Sorry, what? It's a differential form. It is dx13 multiplied by something. All we have done is that, sorry, what was the question? So what I'm saying is that omega restricted on the associahedron is the top form with the coefficient being the amplitude. Okay, yeah.
Phi cube theory, because if I gave you the interaction which was d mu phi squared phi, which is not just phi cubed,
right?
Then
right.
it would not work, right?
Right. Yeah. So what I would say is that a lot of work has been done in these directions. So what happens is that, as of now, I said that this x13 identifies exactly with that x13 that the combinatorial associahedron has. So if you relate this and this in some non-trivial way, what you get are non-trivial interactions, okay? So for instance, Alok in some recent papers, what they had done was that you get Yukawa kind of interaction. So let's say you have phi chi square and so on, okay? By some non-trivial identification of the Mandelstam variables with the combinatorial xi's, yeah. Yes, we get loops, yeah. We get integrand of loop. Yes.
So can you get the loop in 4 minus epsilon dimensions? Like in gauge theories and so on, this might be important.
Right.
To get it in 4 minus epsilon rather than 4.
I would say that we just get.
That's what.
Yes, I hope so. Yeah. So in a way, it's just this that. Sorry, I didn't mean it to be that way. No, it's just that we get in the end what we just try to get are the poles. Okay. So we'll just have 1 over L square and so on. So that is the integrand, and it's in some d dimension. So if you say that we're in d 4 minus epsilon dimension, then it is not divergent, and we can isolate stuff and so on. So actually, there are some subtleties with which dimension you keep. Yeah. Okay.
Where is the information on dimension going?
This looks like dimension independent.
It is dimension independent. I'm saying that it is just in d dimension because all this is just kinematic space. Yeah. Yes. Okay. Maybe I won't have very good answers to that question yet, but we can just talk after that. I will try to get ahead. Yeah. So let me just make an outrageous statement that what are the natural things one can do with a differential form? Okay. So one thing I can say is that I can find the volume of something. That is in a way what we did here. So if we have one form, I can find a one-dimensional shape and find its volume using that one form, okay? And that will be the amplitude, okay? That is what the scalar amplitude is. That is what the original paper in 2017 was about. And now what is the next thing that we can think of? We can contract it with something to get a scalar. And we say that when you contract with something to get the scalar is a gluon amplitude. So here we will see how that can come about, okay? So we propose the following way to obtain the tree-level gauge theory amplitudes, okay? This, where the script P is a differential operator valued multi-vector field. That just means it's a functional over a space of differential forms, okay? Yeah, but it is a differential operators P is a differential operator. Yeah. So to begin with, let's say what is the simplest thing we can think of, n is equal to 3. So if we just have 3 legs, not us, but if the graph has just 3 legs, then the associahedron is a trivial point, okay? It just has 3 outgoing legs. And I say that let's consider this particular differential operator, okay? So what is the idea behind this is roughly in a way you can say that for each, you take the gluon vertex and you replaced each momenta by this differential operator. And why? That this differential operator acting on these poles give you eigenvalue that is xi1 itself, okay? So you can check that this C acting on this object will give you the gluon vertex, okay? The idea behind it just being simply this. You can just differentiate, it is just this. Just this idea, nothing else, okay? We say that xi1, xi2, xi12 are independent of each other. So you can take this thing, you can differentiate this object and you will get the vertex. Mu's are Lorentz indices, yeah.
1, 2 is a Lorentz index, single Lorentz.
Oh, sorry, is it mu1 is a Lorentz index, mu2 is a Lorentz index, mu12 is a Lorentz index, yeah.
Get the vertex from the associahedron, or you got the amplitude?
Oh, sorry, there's no associahedron as of now here. I'm just, okay, so here what I'm doing is just a very simple illustrative thing, okay? So I will go through the associahedron slowly.
So here it seems like you just took the 3-point gluon vertex and just took all the momenta and wrote down these differential operators instead of the momenta. That's
exactly.
What differential operators? The
Whatever he said. Yeah.
xi squared del xi c.
All I'm saying is that if you take this psi c and if you act with this differential operator on these 1 over xi1 square, xi2 square and this, you will get the gluon vertex. Gluon vertex as in you will get this. Let me just write this. We'll get this. It's just a one-line differential. Yeah, okay. And why do we care about it? We care about this that we can write such differential operators for arbitrary graph, okay, such that you get the gluon contributions and all the contact contributions as well. Okay, so the idea behind this is just this, that we don't want to keep the baggage of contact interactions in a way. We just want to have trivalent graphs and we want the gauge invariance to be just satisfied on its own. That is what we want to do. And I claim that using differential operators like this, we can do that, okay?
But this is just giving the 3-point vortex, right?
This is just the 3-point, yeah.
So the 4-point vortex is not part of this.
I mean, if we just have 3 legs, then there will not be any 4-point. That's all. So as of now, here this slide is meaningless. This slide is just yeah. This is nothing. Yeah, this is nothing. Yeah.
Like this is a vertex.
I will get there. That is how I'm answering these questions. Yeah.
No,
Give
but
me a
just
minute.
the statement you had in the previous slide.
Yeah.
Like you said differential operator for arbitrary graph.
Yes.
So let's say I give you some graph. Like maybe I add one more gluon and connect it to 2 points. I have an exchange graph. What does it mean to say a differential operator? That's a number now. That graph, if I contract with external polarizations.
Okay, so let me answer the question this. When I say for a particular graph, I mean like a graph theoretical graph. It's just a graph, no QFT, just a graph. Because what happened was that this subject was, a lot of people were doing a lot of work, and even Kontsevich and Kreimer and all. And to be honest, I will say that that's just above my pay scale. They were doing graph homologies and whatnot, but the crux of their work is something like this, that you take a trivalent graph and you can make something called a Corolla Polynomial out of it. That can be represented as a differential operator, and when that differential operator acts on something, gives us the gluon amplitude or the gluon Feynman diagrams. We will get there. We'll get there.
The graph, The reason I'm asking is
we made
because
the jump from the graph to the amplitude.
sorry,
That is our little contribution to whatever we've done.
I see, but let me just ask the question you can
Yeah.
answer.
Okay.
The question is that, the amplitude, of course, involves the polarization vectors dotted with the value of the graph.
Right.
And there's a lot of redundancy in the value of the graph itself. I mean, that's the whole reason why these amplitudes were first explored. So when you act with a differential operator, do you get the value of the sum of Feynman graphs in some particular gauge, or do you get the amplitude, which is the polarization vectors dotted with it?
So what one has 3 free index, right?
It has 3 free index. Yes. Yeah.
Yeah.
What I'm saying is that you can, as of now, what I will show throughout, and maybe what's written in our paper as well, that has free indices. Okay. N indices. Yeah.
Yeah, that's
Oh, why?
Because there might be terms which, might die when you draw them with the polarization.
Yes. Yes.
So those terms are allowed to exist in the Feynman graph.
I will just say that, I mean, they are gauge redundancies. Yeah. So we just.
Redundant. I mean, you can ask if you contract KMU with this,
Yeah.
whether it gives you 0 or not.
Let me just say a minor. Let me say a minor thing. So if I had shown this C with such that this is epsilon1 dot epsilon2, epsilon12 dotted with this thing, and so on, that will be perfectly all right, right? I just choose. Exactly. Yes. 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 I perfectly agree with you. Yeah. Yes. There's no disagreement over here. I'm just saying.
Unique form, right? You can.
I just say that I've written this up to a gauge redundancy. We can have K-mu proportional terms, but they are not important. I mean, in a way, I can just redefine C such that it's contracted with the external epsilons. Yeah. Okay. Yes.
quick question, like what happened to the Lie algebra structure constants?
Oh, yes. Okay.
That's all
So the thing is that throughout the talk, I will have color ordered amplitudes. Okay. So color ordered amplitudes means what? That you take the amplitude. Okay. Let me write some. Okay. You write the full amplitude as this, sum over all the possible color things, and you will just have to trust me that this can be done for all tree-level graphs for arbitrary n. Okay, and you will always be calculating just this one. Plane. Yes, planar, loop level planar graphs. I just meant to say that if you have loops and if it is not planar, then you will have something else. Yes, exactly. Then you will have multiple trace operators. Yeah. Yes, yes. And really fun thing that happens is that this only has the planar diagrams, as Suvrit just said. Okay, so in a way that if you want to calculate 4-point color ordered amplitude, you will only have S and T channel, you won't have U channel. Okay, yeah. So let me get ahead and do this. So what is this? This is how to construct what I meant here, that I can construct operators for a particular graph. Yeah. So here this will be a quick review of whatever these people did. And this is actually an outcome of maybe a lot of math work, so I'm not sure if I'll do justice to it, but you will just have to bear with me. Okay.
KSVS is also for loops.
Sorry, what it is also for? Loops. It is for loops, yeah, it is for loops. If I have time, I will get there. We have loops. I have loops in my slides as well. Yeah. Yeah. So yeah, so let's begin with this. So let gamma be a simply connected trivalent graph with some number of vertices. Okay, so it is just a tree level graph, just a graph. And what you can do is that let's say that I've drawn examples so that we get an idea of whatever is happening. What you can do is that to each vertex we can assign half edges. Okay, so that if you have this vertex, then it's like you've decomposed the full edge into half edges. Okay, we'll see why that matters. And the edges are directed. For a half edge H on the vertex V, this epsilon is just in a way whether the half edge is incoming or outgoing. Okay, so in a way we can say that intuitively this will have the information whether the momentum is flowing inside the vertex or out of the vertex. Okay, yeah. and each vertex has an orientation, okay, say clockwise. That means that if I take H1, I can ask what is the next half edge to it, whether it is H2 or H3, okay? So if you say it's clockwise, then I will say that H1 plus is H2. That just means that H1 and the next half edge to H1 at that vertex is H2, okay? Yeah, so, so intuitively again, like why do you care about the orientation? Because if you remember, the gluon Feynman rules are just in such a way that it cares up to an overall sign and so on.
You are saying, so what do you do? Suppose I have to take H1 and I have to find the next half. Right?
Yes.
So you move clockwise.
That is just like a choice. You want to be clockwise for all the time.
Which was the arrow is at.
Yes.
You always move clockwise.
Yes, yeah. But it is just that if you move clockwise for this vertex, then you move clockwise for the next vertex and like consistently, that's all. Yeah, okay,
And,
yeah.
have that these arrows are, so what are the roles of the arrows?
Roles of arrows is just that whether the momentum is flowing inside the vertex or outside the vertex.
But that you can always change by taking minus k.
Yes, exactly. So if you do it a minus k, then this epsilon changes and so on. Nothing goes wrong. Nothing. Yeah. Yes. Nothing goes wrong. Yeah.
So you can take the convention that all the arrows are always directly towards Mars.
Yes. We can do that. We can do that.
Vertex, not at all vertex.
Yeah.
Well, you can make sure of that at one
You
vertex.
cannot change the certain orientation in the middle.
No, I'm just saying that for an edge, okay, you can't have. You wouldn't want this. Okay, it's just that it should be this. That's all. Yeah. Okay. So now what you do with it is that you take each of the half edge of the graph and you assign it some variables. Okay. What are these variables? Let's say I call them AH and BH. Okay, for each half edge of the graph. And just bear with me. We're almost there. And now what you can do is that for the entire graph, you can define, this is a Corolla polynomial like this. This C is the Corolla polynomial. That is a product of CVs for each vertex of the graph. So this gamma with this superscript 0, that is the zero-dimensional faces of a graph. That is just the vertices. That just means that you take a product of all the vertices of the graph. Okay, yeah. And then for each vertex, what you do is this. So it's better clear with an example. So these are just some random variables that we assign to each half edge. Okay, yeah. So I would say the simplest example is this one. Okay, yeah. So I will say that this is a graph with 3 half edges, okay, with the vertex V. All right. And what is the thing that I can assign to it? Now, what is the Corolla polynomial for this? It will be this one. B A plus A, B A plus A, B A plus A. All right, with some H1.
Sum is over H.
Sum is over H, yeah.
And half edges.
Yeah, sum is over all the half edges incident on the vertex V.
So only sum over things is common.
No. It's like all 3 of them. All 3 of them, yeah.
But the sign, where is it coming?
Yes, the sign and all comes later on. Okay, yeah.
But then you only have 2, like you put a BH and then in H2 plus H3, why not H1?
Sorry, what? Oh, that is, okay. Wait, let me do one thing. Okay.
Last time minus 8 plus 8.
Each edge takes the right and left one, but not that.
Yes. Okay.
So select an edge, incident on take the next one and the before one, but don't take that. Take only the B corresponding to that. A corresponding to the next one.
Okay, let's do it with a simple thing. So what you do is that you want to write, let's say we begin with H1. Okay, H1. So what we write is we write BH, that is BH1. Okay, then we write AH plus. H plus is 1. H1 plus, if we go clockwise, is H2. Okay, so we write AH2 plus A, H minus is H3.
And you have to do this for every edge.
You have to do with every edge. BH2, AH3, and a third term. So I hope that's what is written over there. And then what you do is you just take a product over all the vertices. I hope that much I've conveyed, because if I don't convey that much, then I've failed miserably. Sorry. No, I would say that they commute.
You can just take them as it's just commutative.
Yes, yes. Yeah. I think so. Yeah.
B is just eta.
Yeah. I would say that this is like a representation. There can be other representations, but I would. So I would say still, let's be. I would still not switch them. That in the end, as a result.
But those A's, all the A's and B's belong to commutative.
Yeah.
The A's,
No, but A's don't commute within themselves.
yeah.
I would say that in general, let's say that they don't commute. Okay.
Okay, so then I should think of them as elements of some non-commutative ring.
I would, yeah, there's nothing wrong in that.
The
Yeah.
ordering will matter, right? How you take the order of product also.
Yes.
Within these, just only commute with other.
Because A has H plus and H minus.
Actually,
Maybe same H minus may appear.
I would,
something
yeah.
else also, right?
Yes. So I would say that it's better to say that they don't commute, as they don't commute.
So then the question becomes, does it matter how I take the product of vertices?
Yes. That's an important question, and I say that it doesn't matter. That is why I was saying that it doesn't matter whether they commute or not.
So I can write this as CV2, CV1.
Yes, exactly. I can write it as a CV2, CV1, and this I can just say that from my observation, I can say that this is the case. That is why I started by saying that I probably won't be doing a justice to the maths that has been done behind. I can't answer whether this is a non-commutative thing.
But if I have a tree with
Yes,
many vertices,
yes.
do I have to at least make sure that the vertices are adjacent, or
I would
just take V1 with some other vertex there, some other vertex there?
That I can assure you that doesn't matter. Yeah. So why? Because
I think some cancellations happen.
no,
Yeah, because this.
it's
by form commutative, but B is by form.
yeah.
That's just B to A plus A
Let
minus.
me.
Yeah, so some of the A will give plus signs and some of the other A's will give minus signs when you try to take them across.
Let me say this. That. Let me say this. That what happens is that these differential operators, now that you're seeing them as a representation, they will be acting on things like where you say that my xi1 2 is independent of xi1 and xi2. Okay, so that if I draw this one, okay, so I will say that this momenta is independent of this one and this one and this one and this one and this one. Okay, so naively you will say that, naively I will also say that, well, that's not the case, like this is P1 plus P2, but I will just say that we start by saying that these are just some variables. This is an independent variable from these two. That's why the differential operator acting on this one, so this is just that.
This is the same differential operator for a given H. That's why
Exactly. That's the thing. Since for a different H, it will just be 0, then that's why it doesn't matter whether they commute.
The same combination will appear. It will appear many times.
Yes.
But it's always the same differential.
Exactly. It will be the same differential operator. It will act in some different order, and since we have this, it wouldn't matter. All right. Okay. So so what we do is this, and now you can see that if you substitute A by this thing and B by this thing, we get this one. All right. And now I say that you can do this for arbitrary graph and get this. All right. Yeah. So now this is.
So if I just do for this exchange diagram.
Yes.
So this should give me both the exchange plus the contact.
We will get there. We will get there. Yeah. It will give us a contribution to the contact thing. Yeah. That is like the punchline of the whole Corolla thing. Yeah. Okay. So before we evaluate these things, let's just say that we can make these Corolla polynomials from the information that the associahedron has. Okay, so what that means is that, okay, a graph being a vertex of the associahedron inherits structures like vertices ordering and edge ordering and everything. Okay, and how do we see that is this, that a complete triangulation of n-gon is isomorphic to bracketing of strings of n letters. Okay, so what that means is this, that you can intuitively see that this bracketing is x24 diagonalization of the quadrilateral. Okay, this bracketing is the x13, or more importantly, I will say that this example makes it clear what the bracketing is with respect to the associahedron. All right. Yeah. Okay. It's just okay. So I would say that if 1, 2 are in a bracket, that means they are two legs of a single vertex. Okay. So if I say that it is 1, 2, 3, 4, I would say 1 and 2 are in a bracket. Okay. Then 3, 4. We don't need to make this bracket because it's understood. Okay. So I would say that you need n minus 2 brackets for a complete triangulation. Okay, and the last bracket will be redundant. It doesn't matter whether you put it or not. Okay.
Why are you calling that x13 and not x24?
x24.
What is the logic of calling the 1, 2 bracket, the 3, 4 bracket as 1?
Do you mean to say that it can? Sorry, what?
Maybe what you're trying to say is that for that graph, if you draw the polygon, then the
Yeah,
diagonal
yeah.
will be 2, 4.
Oh, sorry.
Also, it's not clear.
Sorry. Okay. Let me say this. That this is 1, this is 2, this is 3, this is 4. Okay, so this is 1, 3. That is why this is 1.
Yeah, depends on how you assign the what is this.
I don't understand. Is there some correlation in the
How are you?
ordering of 1,
Okay,
2, 3,
okay.
4 of the vertices of
Okay.
the
So
and the graph itself?
okay, let me say this, that yeah, what you usually do is that you start with the n-gon ordering, one before the ordering of the graph. I don't want to get into why that helps and why that is nice.
Is this a consistent thing to do?
That is a consistent thing to do, and why that, what happens is that you can say that x13 is this. Okay, so, and what you can do is that ij is I plus j. J minus 1, yeah. And this is why you have that kind of ordering. So, okay, I will try to rush, sorry. So what is the point of this ordering? That it naturally induces an ordering on the vertices. Okay, so for instance, you can start from the left, and which is the first vertex, which is the first bracket that you encounter, you call that as the first vertex. Okay, so what I'm all just trying to say is that intuitively you can define an ordering on the vertices. Okay, and that will in turn define an ordering on the edges, and this will also fix how do I make my C from here, in which order do I multiply them. It doesn't matter, but now associahedron will tell you that this is one way that you can do it. Okay, yeah. And also another important thing is that if you fix ordering for one particular graph, associahedron will tell you what are the orderings in all the other graphs. Okay, and how is that the case? Because in another vertex of the associahedron, you draw the same bracketing, and then you can repeat the same algorithmic way, and then you will have an ordering in that graph. Okay, so in a way you have a consistent ordering, and that way you can make these CVs, and then using these representation we can make the differential operators. All right, yeah. So now what we have these differential operators from some information about the associahedron. And let's move on to get the amplitude. So here I will try to give an example of n is equal to 4. N is equal to 4 as in 4 external particles, not yeah. So let's to begin with consider the following expression. So what this means is that now I want to say that this 1 over x13, this is a particular vertex of the associahedron. Okay, so this is a particular graph, a particular. Sorry. Oh, this is not the omega 1. This is one term in the omega 1. Omega 1 will be. Omega 1 is this. This first term will have 1 over x13. Okay. And what you do is this, that you make this differential operator that you make from here, okay, and then you act with this, okay. So what is the point of this exercise? The point is this, that once you have these differential operators, okay, so first this CV2 will act on all of these 5 things, 4 external particles and 1 over this x13. Again, I will now say that this x13 is an independent variable from 1, 2, 3, and 4. We haven't imposed the momentum conservation yet, okay? So what you do is that so when the CV2 acts on this, we get just the gluon vertex over there, okay? All the differential operators. Sorry, what?
x13 can be just pulled across your.
No, pulled across, no. CV2 has the derivatives with respect to that. Okay, so let me say this, that x13 is 1 over xi12's whole square, okay? So differential operators do act on that pole.
So del xi12 will act.
Yes, del xi12 will act on it, yeah.
How did you know how x was related to psi? Is capital
Oh,
X?
that's just my bad. For now, let's just say that this is the case, okay? It's just a notational. Sorry?
xi12 is beyond is what you are calling.
Yes, so as of now, I will say that xi12 is independent of xi1 and xi2. We will impose momentum conservation later on, but that is what the idea is, yeah. So what happens is that once this CV2 acts on these things, you get the usual thing, okay? All the differential operators get replaced by a momentum. But once the CV1 acts on the rest of the thing, it can act on these poles, that gives you the usual vertex. But the CV1 can also act on the CV2, okay? And from there, what you get is this. I'm not sure if I did that correctly.
So you want to think of psi mu as the moment?
Sorry, what?
Psi mu you want to think of as momentum on one of the external legs?
Yeah, so xi's are the momentum.
Psi mu by psi squared.
Sorry, what?
No, xi mu is the momentum of the system.
These are the momenta, okay? All right. And what you have now are these differential operators. And once the CV2 acts on those things, you get this line, okay? But this differential operator CV2, just by simple chain rule, can act on this as well. All right?
There's no such thing as xi34.
Xi34 will be equal to xi12, that's why it's not there, yeah, right, yeah. And once this differential operator act on this line, what you get is just a number. And note that that number will not have a pole in xi12 square. I hope I'm able to.
Don't act on x13, CV1 and CV2.
No, they act on x13. They act on x13. Yeah. X13 is xi12 square. Okay. So those differential operators do act on x13. All right. Yeah.
So this term that you got by CV1 acting on CV2, that part you're saying is the contact contribution is this eta.
Yes, exactly. Yes, it's just pure chain rule. You have two differential operators, and you have to act them on something. So once they will act on that something, that will give you the first term, and then they will act on each other, and that will give you this contact interaction.
Can I just understand? The punchline so far is that you have a set of differential operators,
Yes.
which acting on this product of functions gives you the amplitude or gives you the sum of Feynman graphs. Is that correct or not?
Right.
That's correct?
Yes.
Okay. I'm a little confused about the philosophy because the start of the amplitudes program was that Feynman graphs are kind of the wrong way to do things, because if you look at 4-point functions, The answer is everything is MHV in what you're talking about, and the answer is very simple.
Yes.
But the Feynman graphs give you a complicated answer. Yes. So aren't we kind of defeating that idea of the simplicity of amplitudes is now not going to be present?
Let me say this, that I could have chosen, okay, so let me give me 2 minutes. Okay, I will get there and then I will answer your question. Yeah. So from here, what's the, I will come back to your question. So the idea is this, that if you add these two things now, the two vertices of the associahedron, you get this. I hope that this makes sense.
So x13 is just xi12 whole square.
Yes.
What is x2?
X24 will be, this will be independent of that. Sorry, what?
No, but
what was
that's
it?
what I'm saying. You cannot treat everything.
Exactly, it is just that. So as of now, we say these are abstract labels and we will impose momentum conservation in the end. Yeah, okay?
So in this, the contact term will appear twice?
No, it will not appear twice. The contact term has been split into two contributions, okay? So the contact term is actually the sum of this thing with another thing that is like 2 and 3 flipped, okay? So the contact term has been split, and another thing that the contact term, it's as if it has 3 terms corresponding to 3 kind of color structures that it can have, S, T, or U. So it has split into those channels exactly, yeah. So from here what we get is this, and so the idea is now we can repackage all of this into this, okay? So I call this bracket thing as the differential operator with the external particles outside and here, okay?
Yeah. I understood how you got this last equation from what you did, but okay, maybe a silly question. Is there no U channel?
Is there a? No, there's no U channel because this is a colored ordered amplitude.
Oh, I see.
Oh, okay, yeah, okay, yeah, yes. So in a way, if you add these two things, we have, this is the amplitude color ordered amplitude without the polarization tensors as of now. But what we could have done is that we could have defined our CV such that there are polarization vectors for each external particle. Okay, so yeah, so now I say that this sum I can write as this. Okay, there are too many brackets, but I can write that sum as a contraction of a P with an omega. Okay, how? That this 1 over x13, I chose to write it as a 1 over x13 rather than 1 over xi12 square because I wanted to say that this is a vertex of the associahedron. Okay, so what you took is that for that vertex of the associahedron, you have a differential operator. For that vertex of the associahedron, you have a different differential operator, and you have now combined all of these differential operators into this functional over differential forms, this script P, and this has now these del xi's, such that these del xi's, dxi is like delta, okay? So the amplitude is P omega, okay? And now I come back to your question, yeah. It's just a contraction of a differential operator with the omega, okay, yeah. Sorry, what? Yeah. Yeah. So the thing is, I showed these slides to Alok, and he was very unhappy that this will be exactly the question. That it's a way, in a way, we're saying that, oh, we're just counting up the Feynman diagrams, we're adding them up. I could have started the other way around. I could have started with this, that this is the amplitude, P omega, and I just split P into this, and so on and so forth. Okay. But so what I want to say is that I got the amplitude out of the associahedron by contracting the omega with the differential form. And this is along the lines of the philosophy of the amplitude program. I chose to write it like this so that I can have a little bit of clarity in what I'm trying to say, in how we're trying to calculate stuff.
But the interpretation of P omega,
yeah,
is that you have to first split up the whole thing into some and then apply individual different differential operators on each piece, right?
The thing about that is this, that I would say that P omega is not more efficient in calculating amplitudes rather than the usual things, okay? So I can't take this to my phenomenologist friends and say that I've found something better. I would just say that we've found something alternative. It is, in a way, if you say if I have to calculate amplitude, I would still be calculating the same amount of steps, okay? But it is coming out of something else. That's all in a way. Mm-hmm. Oh, so this is a good point. Now I will say that I never said that K12 is a propagator. I would say that there's no propagator. What I get is an amplitude in the end. There is a pole in K12 square, and that's all. And that is the pole that we want. Yes.
Everything from only trivial graphs.
Yes.
So much less graphs.
No. Yeah. So CVs themselves arrange in such a way. That's a good point. That I never wrote a propagator. Okay. I never said that, okay, I go in a particular gauge and write a propagator. All I said is that I have omega. Omega has the information about poles, and that's all.
But I think the concept.
That I totally agree with you. Yeah, that's a very good point. That is actually something that we're trying to do now. That can we write this mess in the spinor helicity variables to get the neat MHV answer? Yeah. Yes, yeah. That's the whole point. Okay, let me get up here. Okay. So what I'm trying to say is that you take this P. Okay. So I take this P. How do I construct this P? I can construct this P using the information from the associahedron. And I take the omega from the associahedron. I contract these two things, and I get the gauge theory amplitudes. It doesn't. Sorry? Generally, yeah. There are subtleties about D's which are.
That's also, this is indeed more efficient, right? I mean, for some of the items, you just get, if you want like 6-point function of gluon, then just getting like all contact, 4.4.1, everything together, all at once.
No, not all at once. I think you avoid the 4-point part.
Yes.
3-point vortex, you have to
3-point vertices. Yeah. So maybe I can say this, that you only have, that much is there. You only have trivalent graphs. Yeah.
So then to the 6-point function of the gluons, the 4-point vertex will also contribute, right? So you just
Exactly.
not get any of the diagrams which have a 4-point vertex.
Exactly, yeah. So the only trival, because this will capture all of those through this differential.
But you have a way to get like the 4-point.
Oh, they are there. They are there.
The differential operator includes that.
Yeah.
Right?
Differential operator
so
automatically
it sounds
takes.
like you don't have to do any extra work in,
Yes.
like if you just compute the 6-point function from this, a 6-point amplitude from this, it just includes the 4-point vertex contributions, cubic vertex,
exactly.
everything it just gives you.
But cubic vertex, I think the amount of work that you have to do here, because you have to expand it out, right?
Yes.
Or cubic vertex contribution, and to actually evaluate it.
But it sounds
It's a
like
sum
you're
of
starting
terms.
differential operators, right? So you just have the operator.
No, but it's a sum of many differential operators.
Yes, it's a sum of many differential operators, but in a way you can put it in Mathematica.
Yeah, I mean,
and
you just do the sum of
I have
differential
that Mathematica file if you
No,
want to
but
see
each
it.
differential operator acts on different things, no?
Yes.
One is acting on
Yes.
x13, one is acting on x2.
Yes. Yeah.
So it's not that there is one
Then
differential
it's
operator
far
acting.
more easier an algorithm than to compute like 6-point function from, say, for 6 dimensions in where you can't do spinor helicity if you want to compute 6.
I don't agree with, I fully agree with you. Why did I say no? I fully agree with you. I like BCFW, but this is like, yeah. Yes. Yeah. Yes. Yes. So one thing that we can do is we always define those differential operators such that all the external mu's are contracted with epsilons. I think that was just an oversight from our side. We can just redefine the Corolla polynomial or the differential such that epsilons are included. I think now whatever notes that Alok and me we were writing, we always had epsilons because that makes sense. That makes sense. But I would say that we're not missing out on anything by not including epsilons. Everything is still gauge invariant.
But if you have a long string, right?
Yes.
I'm just wondering that in the internal lines,
Yeah.
don't you have to contract the Lorentz indices explicitly?
No. The Corolla, whatever these differential operators, they are they are defined in such a way that takes care of by itself.
Yeah, I guess the point is that you only do like 5 key computations.
Yes.
Amplitude wise.
Yes.
And then you do some differential operation which converts the ABHY.
Yeah.
But all the amplitude computation is just 5 keys. It does not have a format vertex.
Yes.
term only when you convert it, when you apply this.
But for phi cube, you have to think of this as sum over diagrams, and on each diagram you apply the differential operator separately, right?
Yes.
So there are as many diagrams as phi cube.
Yeah, as many diagrams.
It has as many diagrams as phi cube. Yes, exactly. Yes.
So you just do like basic scalar phi cube, then just draw the diagrams for any point.
And then every diagram they have different properties. Apply it,
Yeah.
and
Yeah.
you get a case theory.
Yes.
And
And
includes
yeah.
the vertices, polarization, all these things.
Yes.
And so on.
And
Quite a bit.
yeah.
That's what this
It just reminded me that yeah, we can do BCFW, but that's like there's no connection to positive geometry or anything over there. So that's all that we want to do here in a way. Yeah. Those are different questions. If you ask me how will you efficiently calculate a 6-point amplitude, I would not use P omega. I would still use BCFW. But yes, I am late, but I will try. Yeah. Okay. So now so the structure of associahedron supplemented with the Corolla polynomial can be used to construct CT, which in turn can construct P, and we get the amplitude. So now, does the associahedron know how the gluons interact? Because let me say that, well, what if it is not trace phi square or something? So let me say this, that if I gave the punchline before I said, sorry. So if I define my CV in an alternative way, okay, so that it is not BA plus A in such a way, it is AAA, then it will be, each vertex will be PPP in a way, okay? So what that means, so the amplitude will be that of a trace phi cube. So it can be engineered to have trace phi cube. And if you want to get F cube, yeah, what did I say? Sorry, F cube, yeah. And if you want F4 and so on, then it will be complicated because it's not trivalent anymore. You can't start from phi cube theory and get trace F4 because in a way, the beginning vertex is a phi 4. Yes. Yeah. We haven't worked that out. That's why it's in a speculation sense here. I think it should be doable. You will have different G's for them, and yeah. But we never actually sat down and did those calculations. So I'm sorry. Right. Okay. I don't know how to answer that. Why should it be possible? I can think about it and I will come back to you. I don't know. Yeah.
If you all these differential operators, the intuition for putting a 1 by xi square is the propagator, right? For the mass.
Yes. Yeah, you can. Yeah.
That intuition has value. The fact that it is actually acting on some propagator is 1 over xi square.
How much time can I take? Anurag, how much time can I take?
How much time do you need?
That I don't know. I will try to wrap up in 15 minutes. Is that okay? Okay, yeah. So this is something that we are very excited about actually. Okay, so I would really like to talk to whoever wants to talk to me about this. So can we square up these differential operators to obtain the gravity amplitudes or even a particular graph? Okay. So the thing about gravity will be that you will have arbitrary higher valence interactions. Okay. So if you say that do I have a double copy at at the action level? So that's not understood at all in any way. So here, for instance, I can say that if I have just a CV square acting on these three things, we get the right graviton vertex because that is just a little square of the thing. But do we get the right contact things? So we've been trying out some things, but we don't have very good answers as of now. And I can discuss with whoever wants to discuss this with me. And I will try to catch people as well. Okay, so in the end, I will just say, not in the end for tree level things, what is the exactly. Exactly. Yes. Yes. Not graphs, but terms. Yeah. Yes.
it's somehow, but you're going to get all those problems. Yeah, but if I only has 3, the graphs are very limited for 4-point graphs on any video. You only have a 4-point vertex.
Yeah.
There are 2 graphs. The number of terms you get is very large.
Yes.
Most of them cancel after you contract. And this was David's observation.
Yeah.
This polynomial already knows about gauging variance from these simpler.
Yeah, that is exactly what we have hope for, and maybe it is like a literal double copy that can we just square it up and get something, or like we will talk about it afterwards. Yes, yes, yes. Exactly. So there are different ways in which we can approach this problem. One thing is that you like literally take whatever, what is that called? You take amplitude, and then a bi-adjoint scalar kernel and so on, okay? And then you club them together in some way. So maybe you have C with a kernel inside, but we don't have any answer yet about that. And that will be something really interesting if there is something like that. Yeah, so what is the combinatorics of gluon amplitude? I will say that you have the usual graphs, but now you have things with marked edges, okay? And I am just calling these things as marked edges. This is a marked edge, this is a marked edge, and so on. So what you do is you take each of the contact vertex and you blow it up. Okay, so in a way, if you even take the 4-point gluon vertex, it can be blown up in 3 ways: ST and U channels, and only 2 of them contribute in planar diagrams, and those 2 are here. So these 2 are like these 2 are the marked edges for your associahedron. Okay, so this is what we're calling the layered associahedron. We don't know much about it, and maybe there is something here. Yeah, so now I will do loops in whatever time I have left, okay? So I will try to focus on the Corolla polynomial part of the loops rather than the positive geometry part. And so, okay, so the idea is that you take n-gons, but with a puncture inside them. And then you draw dissections of them, okay? And those dissections will be bijective to the graphs with the loop inside it, okay? What that means is this, that I will call this as a 1-gon with a puncture, okay? Because of puncture, it's a non-trivial thing, okay? And I say, how do I dissect it? I will say that this is a dissection. Why is it a dissection? I will say that this is in a way, pseudo triangulation of the thing. Where is a triangle? This is a triangle. These are the 3 sides of the triangle, and then these 2 come together, okay? So if I draw now a graph corresponding to this, the graph will be this. You put a vertex in each triangle, you put a vertex here, and then things are coming out of each of the edge. So it's coming out of here, it's coming out of here, it's coming out. And then when these two match, what you get is a tadpole, okay? Yeah. So
One dissection from this thing that you draw.
there are so there are subtleties in such a way that you need to so chords can begin or end at the vertices of the n-gon or spiral around the punctures, okay? So it can spiral around as in like this, or it can spiral around like this, okay? So there are 2 dissections in this case, okay? Oh, no. That's infinite. Like that is just the case. It's like the orientation, whether it spirals clockwise or the anti-clockwise. That's
This is what you're going to say is only for one loop?
I want to focus on one loop because at higher loops there are some issues. Okay, yeah. So for one loop we have well-defined polytope. It is called d hat n polytope, and you can write a canonical form just like that. That all the whatever pole comes in, you take a d log form just like that. And this is just a minor aside that it was fun thing to actually think about it, and we independently counted what are the number of vertices of this thing. That means what are all the loop diagrams that you can draw, modulo some many subtleties. Okay, so for instance, if you have L greater than 1, then what you do is just this, that you take n-gons with as many punctures as you have, okay? And then you again draw dissections, okay? So here is an example of what the dissection will be, for instance, for this graph, okay? But when you have more punctures, the problem is that you can draw infinite number of such dissections, okay? So all of these are very interesting things. I'm trying to think of these things, but most of this, sorry, what? Oh, it's just that, so this will be a face of the polytope, okay? Okay, and if there are infinite number of faces to the polytope, it might be a fractal thing. I don't even know whether it is a polytope. All of this is unpublished work of Arkani-Hamed et al. Okay, they're calling it surface hedra, but it has many subtleties, okay? And that's why, yes, yeah. Yes. So I think there are multiple structures here, and one can see how those things are. I think so. I think there is, but I'm not very sure about it, and I wouldn't want to. This is a thing that I don't know very much about it. These are very interesting things, and I'm just showing it here so that just an illustrative example.
For phi cube, for 1 point function, isn't this the only type?
Oh no. Why?
No? Okay. No, 1 point function.
Oh, wait. Anything like this. There are many more.
Oh, you're saying these set of things that you're drawing here, these fractal things will have one of them.
Yes, yeah. But
there's a finite number of
yes, exactly. There are finite number of them, but these will be infinite. So this is a redundancy. You need to mod out with something, and that is like mapping class group. And these are some work by Mariam Mirza Khani and all, and so it's something that is ongoing by them, not by us. That's why I don't want to say much about it, because I don't know much about it. I will just move on to Corolla for loops. Okay, and now let's just say that with an example, let's try to understand with an example. Let's say we have this graph, and I redefine my C like this. Okay, so CV1, CV2, CV3 is just like what we had earlier. So if it was a tree level graph, this is what we would have. And now this is an extra piece. Okay, and this extra piece is defined like this. Why? So that it cancels all the longitudinal modes running in the loops. Okay, so in a way you don't need ghosts as well. You just take the Corolla polynomial, okay, and you draw only trivalent graphs, and it will automatically, this differential, then again you replace A by del over del xi and so on, and you will just like take care of all the longitudinal modes running in the loops and everything.
Now the order in C matters?
No, even now it doesn't matter. Yeah. So our loop amplitudes will be well defined and gauge invariant as well. Okay, so this is the formal definition, which is again just that wherever there is a loop, you have a product of A's and so on, and the CVs which are not in the loop. But this is, I think, good enough. We'll just move on. And now this polytope, D hat polytope, along with the Corolla polynomial, D hat is the one loop polytope.
There is a way to quantize random scale without ghosts.
I mean, yeah.
Because
Yes.
you don't have ghosts here, right?
I would say that, yeah, so those differential operators take care of that. I mean, in the way you just want to get rid of.
Expand out the differential operator, right?
Yes. What you can do is you can identify certain terms after expanding the differential operators as the ghost contribution. Okay. So in a way, it's not something very different from the usual textbook calculations. Afterwards, if we expand out all the terms, because these are differential operators, these will by chain rule expand out. And different terms, we can see that, oh, this is the ghost term, this is the contact term, and so on. Okay. But as a formalism, we don't need to.
Just the repackaging of the ghost Feynman diagrams along with normal Feynman diagrams.
Yeah. So
here's the thing, that the Corolla things, these have a life on their own in some maths literature, okay? And here is what they got. And here, if you just quantize along these lines, you don't need it, You don't need ghosts in a way. And you can relate this with the usual ghosts, and there you can see that, oh, this is maybe a repackage, but that is not the case.
The previous diagram,
Yeah.
why is that H2, H3 and H2?
Sorry? Acha, so I didn't want to have a lot of labels, so I just made them colored.
These are
Okay?
completely independent H1.
Yeah, I'm just saying that red H1 is independent from a green H1. Otherwise, I would have to call it H1 V1, H2 V2, and so on. That's all. I just wanted to avoid clutter. That's why there is color, nothing else. Right. It works at all loops, yeah. So for all loops, yes. For all loops, you can just define a function like this. So wherever there is a cycle in your graph, okay, you just have a term like this. That's all. Even if there are multiple loops, and they just cancel it.
Those diagrams are also there, but they just come out of these different.
Yes.
Like if you come to
Yes.
gluon
Yes.
function, then you get like a ghost loop also, but
Right.
that's also there. That is coming out of some differential operator of this by C.
This is like without putting, there's no
Yeah.
choice of gauge.
There's
How
no
will you
choice of
identify
gauge.
the ghosts then?
Yeah, that's another point. Yeah, because I would say that it's just that this term you are because you know ghost, you are associating it with ghost. In different gate choices, maybe different.
The sum is independent of gauge choice, so it's
Yeah,
how.
yeah. Another one thing. So it's we get a gauge invariant answer. That's all.
And it's not, you're not even at one loop. We know there's a way of reducing everything to boxes, triangles, bubbles, and
Yes, yes.
You really get all kinds of loop diagrams.
Yes.
Arbitrary external.
Yes. Only 5 cube diagrams. Yeah, so there is no bubble, triangle, sum, that would not do. Exactly.
Very complicated.
Yeah.
One loop things, many icons. You know actually nothing beyond the box can actually work.
All those things are still there. Yeah. No. Here it's like whatever 5 cube has, we will again have.
What do you mean by reducible to?
That. Yes. Yeah.
However many point function you have, the one loop basic one loop integrals are only these four and high dimensions. So in D dimensions, that just comes by looking at this is in D dimensions.
Yes.
Yeah, in D dimensions you can have D basically.
Yes. So up to in.
When you have 100 points, you can still have only D basically.
So if you.
Since he is getting the formula for arbitrary D, well, you cannot have that simplification.
Right. Yeah. Yes. If you want to hear about these loop integral things, maybe you should hear my talk in ISC next week. I will talk about this. Anyway, yeah. Another one thing that I want to say, that these much impressive differential operators, these are not our own. Okay, these have been existing in literature since many years, definitely. Okay, what we have done is bring them into the positive geometry thing and say that, oh look, associahedron or these polytopes can make these differential operators, which will give us the amplitudes. Okay, so yeah, so for one thing, that positive geometry identified the common loop momentum across the all possible graphs. Okay, so this is one issue, that if you have different loop graphs, how do you say that this L and that L are same? The loop momentum. Okay, so positive geometry will tell you that this is how you can relate the two. And tadpoles cancel among each other in the Yang-Will diagram, because phi cube will have tadpoles, and when you actually sit and calculate these things, tadpoles will cancel. Okay, so this is the final thing, this is the takeaway thing that we have here, that you start with omega, if you restrict it to some kinematical polytope, you get AN, the phi cube amplitudes. That is what I did here, okay? And if you contract it with something P, then you get the Yang-Will amplitudes, okay? And you can have some differential operator that takes you from here to here back as well. So in a way, you know how to invert P as well. That will be the next slide. Yeah. And this can be done for arbitrary loop, as in modulo those polytope or the positive geometry thing that for higher loop, the thing. Yeah. I should not have written this line. I apologize. So this for arbitrary loop integrands, we'll get this. Okay. So just one final thing, that transmutation. So this is some operation that was defined to take the tree-level scattering amplitudes of one theory backed into another one. This is by Chung, Shen, and Wen in 2017. So the idea is just this. And so they did from amplitude to amplitude. And what we're saying is that you take Yang-Mills amplitude and you get back to the canonical form. Okay? And that you can do easily, and this is just some differential operator. Okay, so you differentiate with respect to all the poles, and then you divide by the numerator. What you get is a canonical form. So this is in a way inverse of the P. Okay, so this is the thing, and I will not talk about this. Sorry, so I'm almost done. So this is the summary thing. Yeah. So the summary is this. So we presented one way to obtain Yang-Mills from the positive geometry. Okay, omega provides the right pole structure, and P provides the gauge invariance to provide sensible gluon amplitudes. And this is the P, just as in, we've seen this now. And the combinatorics capturing the Yang-Mill amplitude is more refined than the ordinary associahedron. Okay, and that is what the layered associahedron. And we write down the curve integral. Okay, so what? So the combinatorics of the associahedron and its close cousins dictate what the functions of external kinematic space are sensible Yang-Mill amplitudes. This is a question that I posed in the beginning, that what arbitrary functions of the external kinematics should be sensible amplitudes, and we have some answer to it. So that the positive geometry can tell you, along with the Corolla polynomial and so on, what the amplitude should be. Okay, right pole structure do not appear by demanding unitarity and locality of the underlying Q of T, but by the canonical form of the polytope, and hence its combinatorics. Okay, and I will end by this. So there are many questions that one can ask now. Okay, so can we obtain gravity amplitude using the action of these Corolla differentials? Will that be an off-shell double copy at the Lagrangian level? Okay, or can it tell us anything new about renormalization? Okay, because there are a lot of Hopf algebra structures that are there, and can we do that now? Can it give us anything new? Or can the Corolla differential operator spin up arbitrary amplitude, say Venezian amplitude? So if I take a string amplitude, the world sheet integral, and in the integrand, I put up a differential operator. Can I engineer a differential operator in such a way that I get maybe the gluon string amplitude? I don't know the answers to those, but these seem good to me. And how does it connect to the other works that are being done in the similar area? So that's all. Thank you. Thank you for your attention.
Questions?
Big question. You know, in the end, there was an effort many years ago to, so this is very nice, but the question is, there's an effort many years ago which was to try and understand field theory in terms of diagrams. But then we realized that, you know, sometimes there are non-perturbative effects and so on, which diagrams don't contribute, and in the end, they'll only give us an asymptotic series. So is there since you're trying to find a reformulation of field theory, right? You're trying to say some positive geometry that plays a role as opposed to unitarity and so on. Is there some hope that you will get some action principle, something which is more fundamental than diagrams using this, that somehow positive geometry is going to capture everything? Is that the hope somehow? Or?
Yeah, maybe one can say that, because that is probably the case in the amplitude-hedron. That is the case in the amplitude-hedron. That that you don't care about the action principle and stuff, and yeah. Yes. Let me say this, that for instance, the amplitude-hedron, what it will give you is that the tree amplitude-hedron will give you the tree level n is equal to 4 amplitude, and it will not have information about the individual graphs at all. Yes.
Theory, because that's only an asymptotic series in the coupling constant. Okay. So in the end, the action tells you a little bit more. It tells you I can put it on a computer and really calculate if I had a strong enough computer. So there's a non-perturbative definition of the theory which is not captured by Feynman graphs.
Is the question that do the on-shell amplitude have the full information about the theory? Or?
Well, if you give me the S matrix, it probably does. But the perturbative expansion of the S matrix clearly doesn't.
Okay.
I think it doesn't. How would it?
Yeah.
Just asking whether he can reproduce non-perturbative factors or not.
Yeah, but that's because you want to reformulate quantum field theory, right? That's the big program.
Replace path integral by itself.
Yeah, so that's what is the program.
Yeah.
The
No, those,
That also has a non-perturbative.
yeah, those are, I think, big open questions. For instance, if you say that can I get some off-shell correlator or maybe even an out-of-time correlator out of
I think
them?
what is just not optional. Just S matrix itself.
S matrix, just get the S matrix.
Okay.
But normally, because of an asymptotic expansion,
Yeah.
you know that by itself doesn't
Converge.
converge, right?
Okay.
You have to, and that indicates that they are also non-perturbative.
Right. Yes, yes. So,
if you are an action principle, the same action will give everything, right?
Right,
Perturbative
right,
answer as well
right.
as the instantons.
right. I would say that maybe you are always around a particular well-defined vacua. Because if, for instance, you have instanton, what will it mean to say that I have particles around that? I mean, no, it will have a different notions of maybe that.
Let's say you took a 137-point amplitude in quantum electrodynamics.
Right.
You'd never be able to calculate it perturbatively because perturbation theory would just break down.
Right.
Because you're coupling constant 1 by 137. Alternately, if you try to compute 2 to 2 amplitude beyond 137 loops,
Right.
it would never work. Like your perturbation theory would start growing. So you're a well-defined vacuum. It's that's the law. Yeah, nobody's computed, all right? But nobody has computed. Yeah. But there are pretty good arguments that suggest that this should happen. So somehow there should be. Because it's such an ambitious program and not just a question of reformulating, you're trying to, that's for your last slide. So is there any understanding of how this might happen, or you're saying maybe not right now? Maybe there isn't.
I wouldn't know how to answer that question.
But we hope that somehow reformulating diagrams will then lead us to some principle that will capture everything somehow, right?
I would say that the whole idea is not to see it as a reformulating of the diagrams. I mean, at least here
But you are still reproducing order by order, right? That's the
yes, that's the point. Yeah.
Whereas what we want is something which goes beyond doing it order by order.
Yeah, that is there. Yeah.
I mean, an action principle in principle
Yeah.
is not an order by order.
Yes.
I mean, you can just put it on a computer.
Yes. I think we will. I think.
Canonical quantization also you put in principle solve the Hamiltonian.
I think you will always miss the non-perturbative effects using these things. I think that's what I think. Okay. Right. That I agree.
Principle of positivity or whatever. Give you the non-perturbative definition of the S.
Right. So because I think most of these methods or all of this rely on beginning with what are my external scattering states, okay? You always begin by saying that I have 4 particles and with this momenta or with this polarization, whatever the scattering data is. And then you do whatever you do with it, okay? So in a way, if we say that non-perturbative things, I don't know how to begin even ask. Yeah. Right. Right. Whatever. Right. I think that will be the ambitious question that at least now I can't even imagine.
Any bootstrap, for example, is
Yes.
not one. Right?
Yes.
You are not.
Yes. That is like the full amplitude, whatever the amplitude is, not up to a particular loop, the full answer, whatever it is. Yeah. So maybe along the lines of bootstrap or maybe using those principles as well, maybe we get some non-perturbative ideas about the S matrix.
Okay, are there any more questions? If not, then let's thank the speaker once again.
Thank you.